started. Today, everybody is here to learn a little bit more about cognitive services. So who here has seen cognitive services in action before? Few hands? All right. Who here has been kind of ingrained in the machine learning and AI track all day? Cool. So you probably saw something very similar to this from AWS in the morning. In this iteration, we're going to be going through a lot of code samples, so I'm not sure how much of that you got. A lot of use cases, and a lot of kind of machine learning and deep learning background. So if anything was very fuzzy, kind of from a theory perspective, hopefully that'll be cleared up by the end of this lecture. And who am I? I am Paige Bailey. I work for Microsoft. I have about 10 years of experience with Python and about 5 years of experience building predictive models with things like scikit-learn, TensorFlow, using Keras as the developer-facing front end. I spent 5 years in the energy industry before coming to Microsoft, so this is kind of my bread and butter. This is actually the first time I've given a presentation without talking about building deep learning and machine learning models from scratch. So today, this is going to be the easy, well, not easy. This is going to be the straightforward fun stuff. So how do you get to leverage deep learning models that have already been created, that have been trained on 14 million images or corpuses of data that are terabytes in size? How can you leverage those without having to pay a lot of money up front for hardware, for data storage, or for machine learning engineers, because machine learning engineers are all very expensive. And that might be why some of us are in the room today, right? Is like you saw some salary postings for data scientists and you're like, oh yeah, definitely. I know that was me. I was just like, yes, data science. Absolutely. I'm also Dynamic Web Page on Twitter. So if you want to tweet anything or if you want to go investigate my GitHub, I'm pretty much Dynamic Web Page everywhere on the internet. So to get started, what are cognitive services? Then we're going to be talking about how they're used and then how you can get started with using them. But to start, I'd first like to go into what exactly is artificial intelligence. That gets thrown around a lot as a buzzword, and there's not often a lot of clarification as to what the industry means as to AI. So artificial intelligence has been around for a while. The textbook definition is that it's any technique that enables computers to mimic human behavior. And if you go by that definition, AI's been around for a long time. It's been around since the 50s and 60s. And back then it was something called symbolic AI. So the idea then was that every single rule, every if-else statement that would take to control an artificial intelligence, you, the developer, would have to explicitly program. So if a robot came up to me and said, hey Paige, tell me something to do, and I said, give me a cup of coffee, then I would have to program every explicit if-else statement for that robot to complete the action. Or if I wanted it to understand what a photo of a cat would be, I would have to explicitly code in every bit of information that I knew about a cat. So since then, symbolic AI has been disproven because it just doesn't make sense, right? There's no way that we as humans can know every single explicit rule that it would take to solve every possible interaction that you would have with an artificial intelligence. But from a machine learning perspective, it gets a little bit more interesting. So AI, big bucket. Machine learning is a subset of AI. And what that really is the ability to learn without being explicitly programmed. So what does that mean? Right now as developers, you have data, you have this logic that you formally encode into a program, and then you get back some sort of output, some sort of response. Machine learning, you have your output that you want, you have data, and you give that to the computer and it gives you back the rules, right? So instead of you having to explicitly code, you get back the program that would be required to give you some sort of output. And this is kind of a very simplistic overview of what machine learning looks like as an ecosystem. If you go on scikit-learn's website, you'll probably see something a little bit like this. And machine learning is divided into two real classes. supervised and unsupervised. There's also a class called semi-supervised, but that's kind of getting into the weeds, and we might talk about it a little bit later. But a supervised learning problem is you have data that has been tagged. So you have pictures of cats and somebody's, labeled them as cat, or you have, a bunch of voters and somebody's labeled them by political party and you have a bunch of information about them. But whatever it is, your data has been tagged. And if that's the case, then, lucky you, right? Like supervised learning is very, very straightforward to do. And most of the deep learning and machine learning research that's been done and case studies that have been made and business value that has been created with supervised learning problems. So for classification problems, that's those categories that I was talking about before, right? So cat versus dog. Voter A political party versus voter B political party. Or you could have something called regression, which is basically just trying to predict a numeric value. But classification, categories, regression, numbers. And then you have a bunch of algorithms that fall into those categories. If you don't have labeled data, then you have to do something called unsupervised learning, and that's a headache and a half. Most unsupervised learning problems, you're better off with just hand labeling data or getting Mechanical Turk to do it for a month instead of trying to spend 6 months trying to do a clustering problem for an unsupervised learning task. So today we're going to focus more on supervised learning. And that's been a lot of words on a slide, right? And that doesn't necessarily make sense to anybody. So let's try an example. So say your boss comes to you, you work for a bank, and he gives you a CSV file, because it's always a CSV file. And it has a bunch of information about your customers, right? So it has their age, whether or not they have a job, whether or not they own a house, their credit rating, their education, and then whether or not they defaulted on a loan. So whether or not they paid you back the money that they were supposed to when they were supposed to. But if you're my boss and you're the head of a bank, all you really care about is that last column, right? Like, did that person pay me back or not when I loaned them money? And really, really, all you care about is what is the likelihood of a default from this new potential customer, this 35-year-old who has a job, who does not own a house, who has bad credit, but who went to college. What is the likelihood that he would pay me back on time? And you can do something like build a decision tree. A decision tree is a kind of classification or regression algorithm that you can create that looks a little bit like this. And it has a series of nodes. The nodes ask questions. You follow those nodes through based on the answers to those questions. And ultimately, you reach some sort of assessment, some sort of classification as to yes or no, this person should be given a loan. And if we follow it through for our guy, we get this, right? So he's in his 30s, he doesn't own a house, he is educated, let's give him a loan. And that would be the assessment that's made. So this sounds very much like if-else logic that I was explaining before. And I think this is one of the best first examples that you can see for a machine learning task. And also, I'm of the impression that whatever I show you, if I don't show you code, then it doesn't really count. So let's go and look at some code. If you follow this link, you will see every single demo that I show you today. And it also should have some pointers to additional reference materials if you'd like. The slides will also be posted to this link too. So let's go and take a look. Excellent. So this is the repo that you should find. And if you click on the GOTO Amsterdam 2018.ipy and b file, it should take you to an Azure Notebook. So how many of you have played with Jupyter Notebooks before? Several hands? All right. So for people who did not, that is your homework for today. You should go and take a look, and you don't have to pay any money whatsoever. Project Jupyter Notebooks are fantastic. They are interactive programming environments for a variety of languages. So for things like F#, if you're a C# person, Python, R, Ruby, Julia, you can just download kernels for specific languages and then use this to immediately display the output from your code. And so what that looks like in practice is you have cells. So if I double click on one of these cells, there we go. It turns into Markdown that was used to generate it. You can change it dynamically. So if I wanted to remove this line, right, and just click Shift Enter, it would use it. If you want to install packages or load them, you can also change the code that you have in the code generating cells. And what we're doing here is and I apologize about the resolution. Usually I zoom in with my laptop, but I don't think this one's a touch screen. This is a CSV file filled with all of that data that we were pulling in for those loan folks, right? So we have a CSV with a bunch of columns, a bunch of features, talking about different records, different people that we have in our data set. And we have things like checking balance, the month loan duration, their credit history, the purpose of the loan, the amount, the savings balance, and then also the data type associated with each of those features. And anytime a machine learning engineer tells you about a feature for their machine learning model, just think of it as like a column in a spreadsheet, right? Unless it's a vision task, and then it might be a little bit different. But if they're talking about alphanumeric data, just think of it like a column in a spreadsheet. You can get some idea of the different proportions and distributions that you have for your data. You would divide it up into a training and a test set. Usually there's a training set, a test set, and a validation set, or you would do something called cross-validation, where you iterate over those values over and over. And then you would actually go about building your model. And the thing that I want everybody to focus in on is that to build a machine learning model, to make a prediction with R, which is what this language is, it takes one line of code, and it's that one that I highlighted. So to generate a predictive model using a machine learning model called C5.0, C5.0 is the standard for decision trees. It takes one line of code. And it's very, very similar in scikit-learn. You can do amazing things with less than 10 lines. With Keras, which is a developer-facing API for TensorFlow, you can do similar things with less than 10 lines of code. But again, very, very straightforward. You don't have to be the person explicitly coding all of the math. And what this does is it creates a decision tree for you. You can see the output displayed here. Each one of these is a less pretty version of the decision tree that I showed you before. So these are the nodes, and those are the branches. And you can see that again, just one line of code created all of the if-else logic that you would need in order to make these assessments. And the error rate is only 13.9%. So it's a pretty performant model. You're able to cover most of the attributes that you see. If you wanted to improve performance, you could add a whole bunch of models together. This is something called adaptive boosting. So just think of it as a two heads, multi-heads are better than one, right? So if you add up a whole bunch of models, pool them all together, you can understand which nodes were more effective and which weren't. And then you build like a super collection of trees, and it can give you even better performance. So that's creating a machine learning model on your own. That is all open source technology, all using Azure Notebooks, and relatively straightforward to do, but it still takes a little bit of time. So where could that break down? Like why would that be problematic for folks to use? And it's for a variety of reasons, right? So as we cycle through all of the slides, because your data usually looks more like that, right? Like it's never very clean. The CSV that I showed you was very straightforward. It had, the names explicitly stated. It had all of the data in a friendly format. Most of the time, it's not like that. Your data is also going to come in a variety of sources. So it might be XML files that you have to parse, or JSON files. It might be tables in a database somewhere. It might be CSV files. It might be, scraping web pages and doing that on some sort of frequent basis. It might be pulling in streaming data, and it's highly unlikely that all of those would have a consistent key. So you might have to map whatever your loan grantor, your loan applyee, to some sort of username or some sort of like social security number if you're operating in the United States. And then also, what about combinations of features or other features? So we just had one CSV file. It might be that the best predictor for this model would be something else, something that we didn't even think about including. So if you want to pull in that feature, you would have to go as a creative data scientist and ask your boss if there was a location where that feature was located. So the takeaway is that traditional machine learning can be extremely effective, and it requires less hardware than deep learning. So you can do it on an Azure Notebook in a browser using just CPU. But it also requires a lot of data engineering work up front. And it's best suited for well-defined problems for data that is largely alphanumeric. So you probably wouldn't want to be using this for things like images or video or sound. So it's still useful, it's still extremely useful, but it's not really the ticket that's got everybody excited right now. And what does have everybody excited is something called deep learning. And deep learning is a subset of machine learning, so big bucket AI, machine learning subset of AI, deep learning subset of machine learning, that is all explicitly focused on deep neural network architectures. So everything that you see that is touting that it's a deep learning framework, a deep learning tool, is leveraging things like LSTMs, convolutional neural networks, RNNs, and else on the back end. So chatbots, that's deep neural networks. They're just leveraging natural language processing techniques for them. And it does, so deep learning's got everybody very excited. Why? Because you can do things like automatically detect entities in images. You can detect specific people using just a few images as a training set. So if you had a corpus of all of your employees at your business and you wanted to be able to pick out specific people in a video, you would be able to train it using just a couple of images that you have from badges from your employees. You can also do things like automatically detect tumors or cancerous cells just by looking at x-rays or just by looking at sort of microscopic images of those cells. And the way that you would do that with a deep learning architecture is, again, not a whole bunch of lines of code, just having two folders, one with a bunch of files that are cancerous and one with a bunch of files that aren't quite, and then pointing your neural network at them, and the computer figures out what constitutes a cancerous cell and what doesn't. You can also do really interesting things with text. So this is kind of a joke example, but if you gave all of the text of Harry Potter books to a neural network, it would generate a title, something like Harry Potter and the Portrait of What Looked Like a Large Pile of Ash, which sounds reasonable, based on historic titles. But you can also do things like take hip-hop lyrics or rap lyrics and turn them into the style of William Shakespeare, or other things of that nature. So it gets really interesting. And also projects with sound. So Magenta is a great project from TensorFlow where you can create music and art using machine learning. If you give all of the 8-bit tracks from Mario or from Legend of Zelda to it, it can start creating its own 8-bit music for your video game. Or you can strum out a melody on your guitar and it automatically creates, drum accompaniments or a bass accompaniment. It can also do things like speech to text. So as I'm speaking English, it could automatically transcribe what I'm saying into English words. and then translate it into, you know, whatever language you choose. So it could be Dutch, it could be German, it could be Klingon. If you're like a Star Trek fan, that is an option. Anything that you wish. And a whole heck of a lot more. So here are just a few examples. You've probably heard about AlphaGo, which is using kind of neural networks battling each other in order to beat the game. Mona Lisa juxtaposed with Starry Night. So you take the style transfer approach of one artist and place it on another. Autonomous vehicles, lots and lots of use cases. And it's become so popular recently because it's more accurate than humans at classifying images. There's this guy named Andre Karpathy, who's now the head of data science at Tesla, and he was a grad student, and one of his projects as a grad student was to go through an extensive image set, so like tens of thousands, hundreds of thousands of images. And as a grad student, he would just sit there saying like, this is a cat, and he would label it cat. This is a dog. This is a horse. On and on and on, which sounds like a, you know, like a delightful university education. But he was accurate, I think something to the effect of like 93% of the time. You know, it was in the mid 90s that he was accurate. And now we have neural network architectures that are better at classifying images than Andre Karpathy was. He is our human benchmark, and maybe he's just like really bad at classifying images, I don't know. But now you have neural network architectures that are better than him. We're also better at language translation, and better at voice and sound. So if everybody in the room started speaking all at once, it would be really difficult for me to pick out somebody like one single voice in the back, but a neural network architecture could do it very easily. We also have very specialized hardware that allows us to train networks faster than ever, and more performant. So things like TPUs, which are custom ASICs, custom silicon chips where the algorithms are actually burned into them. Also things like FPGAs, which has been kind of Microsoft's chosen approach. So FPGAs are really great for speedy inferencing, so being able to get an image and tell you what it is immediately. TPUs and custom ASICs, they're a little bit speedier at the training side, but they're slower on the inferencing bit. And then also GPUs, they're getting better every day. If you have friends who are Bitcoin miners, you probably know that they're really getting difficult to find in just like run-of-the-mill stores. And we also have lots and lots of data and lots of frameworks that have been open sourced as packages. So again, scikit-learn, TensorFlow, Keras, all that good stuff. So getting started with artificial intelligence. You know, we've talked about what it is, so machine learning, and then deep learning as a subset of machine learning. If you wanted to get started with it, you would either need to create your own model from scratch, or you could just deploy somebody else's that's already been pre-baked. And creating your own model, it takes time, usually to the effect of weeks and months. It takes data, usually in millions of classified inputs. It takes experience in that you need to employ like very expensive machine learning engineers. And it also takes hardware. So again, GPUs, TPUs, FPGAs, and those are all very expensive in and of themselves to purchase. And just to kind of go into why you would need it is because GPUs are designed for these very parallelizable workloads. And neural networks are layers of nodes that are all doing the same thing. So if you have layers of nodes all doing the same thing, it's really easy to break out those same things into a bunch of different chunks and put them through a GPU as quickly as possible. So you have a CPU for all of the sequential tasks. You ping a GPU whenever you need performance for the neural network architectures, and then back to CPU if you need to do more sequential stuff. Quantum computers would work the same way. So we would leverage a quantum computer in the same way that we would leverage a GPU, and TPUs operate similarly. And FPGAs and custom ASICs, again, I just mentioned. FPGAs, they offer a lot more flexibility, but you have to explicitly program how they handle your algorithms. Things like TPUs, they have the algorithms already kind of burned into them, but that means that they're very, very good at one kind of neural network architecture and not as great at another kind, and there's no way to go about changing it. So these are data science virtual machines are just kind of a plug for Azure. If you want to get started with all of those packages that I just mentioned and that I'm about to mention, data science virtual machines are a great way to get started. They're also free for your first year of using Azure for just a CPU machine. So if you provision a CPU machine, then you get all of these packages downloaded for you and ready to roll, and all of the dependencies managed. And if you've ever worked with Python, you know how much of a headache it is to manage dependencies, especially for scientific packages. Machine learning models usually built with things like scikit-learn and Caret if you're using R. Deep learning frameworks usually built with TensorFlow, MXNet, Cognitive Toolkit, and PyTorch. And so most of the models that I show you today are going to be built on top of either TensorFlow or Cognitive Toolkit. But again, if you don't want to have to worry about building it all yourself, you can just call somebody else's model, which usually takes less time, it takes less data, and it takes less hardware. Usually no time, no data, and no hardware. And that's where we get into cognitive services. So say you have an idea, right? So say you have a favorite movie, and you want to put some sort of emoji mask based on the emotions of the characters for this movie, right? So based on this, Leia looks pretty dang angry, and Han looks just kind of frustrated. So that seems like it would fit. Or say you have a great idea where you have a phone app, and you want to put puppy faces on people because apparently that's what all the cool kids like is putting puppy faces on people. Or you have another great idea where you want to take a baby and put Harry Potter things on baby faces. Because venture capitalists would be all about funding that, right? Or say you have another bright idea. You want to be able, you watch your friends and they're dancing and they look kind of stupid, and you think, well, who else, is kind of stupid, and you just put politician faces on your friends as they dance, right? So just kind of that general idea. And so this all seems very complex, right? Like it would be a tough task to manage, but in reality, it's actually quite simple. Because guessing placement on people's faces is a known task, right? So Apple does this all the time with its face unlock. We have it for Surface Books to do face unlock. And all you're really looking for are specific locations on people's faces. So like right nose, left nose, top lip, bottom lip, eyebrow locations, forehead locations. And you're just placing some sort of image on top of those specific locations. So it doesn't matter if it's a puppy mask or a Harry Potter face or Trump's face, though, God, I really hope that nobody does that. It's just a simple known task. And the good news is, too, is that all of those things that I just mentioned have code that's been open sourced. So these are two members of my team, Suze Henton and Asim, and Suze already created the emoji mask feature for browsers. So it turns on your webcam, and based on the emotion that you show on your face, it places an emoji that matches. Or Asim created a thing called Smile to Unlock, where if you want to unlock your laptop, you have to smile at it, which gets really annoying if you haven't had coffee. But it's really simple how they went about architecting those solutions. And this is an example of a chatbot that I created for a music concert in the United States that was just pointed at an FAQ page for a website, and it automatically generated natural language responses based on those questions. And the question that probably all of you guys are asking is, well, how much code does it actually take to do this? And the answer is like that, right? So that's two examples And that's all the code that it would take to create the emoji mask, or the chatbot, or some sort of language translation system. It really is less than 10 lines. It's just a REST API call, and you can use any language that you want, right? You can use Python if you're a Python person, but you can also use things like Java. You can use C#, you can use Ruby. Anything that you feel comfortable with, you can use. And like I said, it doesn't matter unless I show you code, so let's go look at code. And these two are examples from my personal GitHub. And again, I usually kind of zoom in, so I'm not sure if there's a zoom in feature on this laptop, so we'll just have to make do. But this is an example of using the Cognitive Services API for bacon classification. But not bacon, it's more like Kevin Bacon. So Kevin Bacon is an actor from the United States who's been pretty active for the last few decades. And I thought it would be really interesting to track Mr. Bacon's age over time. But I wanted to learn a little bit more about him too. So not just his age, but as many other attributes as I could get about him from just images. So you can see here that in our request parameters, we can ask for age, we can ask for gender, smile intensity, so from 0 to 1 how happy a person happens to be, facial hair and the different kinds, so like mustaches, beards, sideburns, head poses, whether or not they're wearing glasses and what kinds of glasses, their hair color, whether or not they're wearing makeup, whether or not they're wearing accessories, whether or not their face is occluded, so if it has some sort of blockage, and then also noise levels. And I want you to count, again, how many lines of code it takes to generate this, right? So we just import some libraries. We have a subscription key and a header file, or just a little header dictionary, basically, for Python folks. We have parameters, again, just a dictionary of parameters. And we have some pictures of Mr. Bacon, over the years. He has aged so gracefully. And then all you have to do is create a try and accept statement using that header and using the request parameters. And it gives you back a ton of detail about the image that you submitted. So again, all you're giving this is a single image, nothing else, just a link to a JPEG. And it gives you back an estimated age, so 29.1. It gives you back emotions, so percentage anger, contempt, disgust, fear, happiness, neutrality, sadness, and surprised, facial hair, gender, hair color and confidence levels for each, and then also those XY locations on the image as to where eye right outer, eye right top, eyebrow left outer, all of these different kind of pinpoint locations happen to be. So that's kind of magical, or at least I think it's magical, right? Like all you have to do is give an image and it can tell you everything that you would possibly want to know about the person that you have in that image. And if you have more than one face within an image, it does this for every single face that it can detect with a single REST API call. Another example that I was doing for the Nature Conservancy was building out a proof of concept for an application called Mapping Ocean Wealth. And what Mapping Ocean Wealth does is it uses Flickr and Instagram posts, so images that have been uploaded with geotagged coordinates, so you have lat-long coordinates for each. And it uses that as a proxy to detect tourism activity. So why is that important? If you have a nation like Belize, say, that has a lot of coral reefs, all of them in various sort of levels of endangerment for extinction, it makes the government kind of sit up and take notice if you can say, look at this, 80% of your tourism activity for this month seems to be caused by reef-related activity. So if you can look at all of these images that have been uploaded to social media sites, get the geotagged coordinates so you know where they were taken, and then pick out all of the ones that are reef-related, you can use that as a proxy for tourism activity. And then that can be used to fuel policy discussions that can help with things like climate change. So it's really, really important. And it's also really, really unfair to ask a grad student to go and hand tag, oh, this is a fish, this is a coral, like this is definitely reef related. You know, like somebody's sipping a margarita on the beach, that's probably not reefy. You know, those sorts of things. So for them, I used the Vision API, which is similar mentality, right? So just import some libraries, have a header, some parameters, and then it gives you back all sorts of information that you would have about that image, including a plain text description. So you can see here that for this image, we got back a group of colorful underwater, and we also got back some tags like reef, colored, surrounded, nature, covered, colorful, and different tags for confidence levels. You can also do things like scuba divers, and if you wanted to stress test it, this last example is a man flying through the sky, right? But he looks pretty similar to that scuba diver, right? So, you know, blue background, similar, you know, goggle situations, similar gear. But Vision API was able to pull out that it is a man flying through the air on a cloudy day. I'm not sure how easy that is to see. But it is a man flying through the air on a cloudy day, as opposed to a scuba diver, or I think the label that was placed for this was a group of people swimming in a pool, right? Versus a man flying through the air on a cloudy day. So those are just a couple of examples as to what you can do with the Face API and the Vision API without having any sort of understanding of machine learning in general. And would somebody help me out? Which is the one, like, start from this slide? Is it second one? Awesome. Perfection. Excellent. Thank you. I appreciate it. So how many different cognitive services do we have? There are quite a few. Right? So we have the computer vision API, we have content moderation, which can automatically detect if somebody like puts a scandalous photo into one of your comment fields on your website. We have the video API, which is basically just like throwing every cognitive service that we can at videos. So you automatically get speech to text transcription, you get description of the video, you get translation if you'd like, you get how many people are speaking all at once. The video indexer, the face API, the emotion API. You can even do custom vision services. So if you want to be able to pick out, say, you know, you were looking at Star Wars footage, and you wanted to be able to pick out BB-8 versus, you know, R2-D2 or C-3PO, you could train some images to understand what C-3PO looks like, and what R2-D2 looks like, and what BB-8 looks like. And you only need 5 for each, and it would be able to automatically pick those out in images. You can do things like translator speech, knowledge, recommendations, language understanding services. So those are what fuel the chat bots. Text analytics, so being able to automatically extract keywords from text. You can do things like knowledge search. And then also other topics such as labs. So cognitive services labs are a variety of projects. They're in various stages of completion, but a lot of them are focused on sort of preferential routing. So say you had a fleet of trucks and you wanted to be able to get them from point A to point B with some constraint. So you wanted to be able to hit, say, the most customers on the route, or you wanted to be able to only go on roads that supported trucks that had a certain weight, you would be able to use these cognitive services in order to do that. And then a new one that was just announced at Build is something called cognitive search, which is an AI-first approach to content understanding. And what does that mean? It's basically taking every single cognitive service that we have and throwing it at the data that you already have stored on Azure, which is our cloud platform. So if you have a bunch of CSV files and blob storage, or if you have a bunch of PDF documents, what this would do is it automatically scrapes the PDF documents, so it extracts all of the text. It does keyword extraction, so it picks out different entities within the text. If there are any embedded images, it describes the images and picks out keywords associated with that too. And then it builds a knowledge graph of everything that you see. So what does that mean? The example that we showed at Build was an NBA use case where and NBA is kind of the basketball league of the United States. They had a bunch of players, a bunch of pictures that they had taken of players, and there was a link in this node graph where you had a player's name and then also Nike, which is a brand of shoes, and they were connected really, really strongly. And when you pressed on it, you were able to see that the relationship between that player and the shoes was that even though there were no text descriptors of this anywhere, it had a bunch of pictures of LeBron wearing Nike shoes. And it just automatically detected that that was the shoe type and that was him. So, live demo time, always dangerous. Let's go and take a look at something called the JFK files. And this link should be in the repo that I was just showing you. So if we go to the JFK files web app, I also want to make sure that you guys see the GitHub repo for it. All of the code used to generate this website and also a short description is listed here. But the JFK files, JFK was a president that was assassinated in the United States halfway through the 20th century. And all of the files associated to this case were released. Problem is, most of them are images, most of them are PDF documents that are scanned and of really poor quality. So if you want to understand kind of the entities associated with that assassination, it gets a little bit tricky if you're just doing it by hand. But if you use something like cognitive search, and I search for Oswald, who is the assassination, the person who did the assassinating, you can search through every single file associated with that tall order. And this is going through, you can see there are 857 results found for Oswald throughout this. It can automatically detect the name written in handwriting. It can detect it in terrible quality in a PDF document. And it can also understand that that is his image in a police photo. So lots and lots of examples. And if you want to play around with any of this yourself, this is freely accessible online. I encourage you to do so. But in the interest of time, since we got started a little bit late, I'll try to cycle through it a little bit quicker. Excellent. So if you want to learn more about artificial intelligence, there are a few options. And a lot of stuff on the internet is really, really terrible. Like very, very bad, not useful at all. But there are some things that aren't. And Andrew Ng's Coursera courses on machine learning and deep learning are fantastic. If you complete those, you'll probably have a solid understanding of the mechanics of what's actually generating neural network architectures. I also recommend the Introduction to Deep Learning from MIT, Data Camps courses, they're all fantastic. There are a couple of textbooks that I have listed here, so Artificial Intelligence, A Modern Approach, and also Scikit-learn's documentation. And then if you want to get your hands dirty on actually training networks, I recommend Kaggle. There are a lot of examples on notebooks.azure.com, which is what we were using for that link today, TensorFlow Playground, and then also attempting your own deep learning project. But if you just want to incorporate deep learning or artificial intelligence into your applications, if you just want to be able to recognize entities in videos, or if you want to be able to recognize specific things in pictures, or count the number of people in crowds, or if you want to be able to take speech to text and translate it, then all of those use cases have already been very well defined. They've been trained on a massive amount of data from either Microsoft or from AWS or from Google, and you can just ping it as a REST API instead of trying to architect your own solution on a much smaller set of data and probably not achieving the same accuracy. So thank you so much. I think I stayed on time as well as I could. There's another example that I didn't get into that's listed in the repo, the Contoso B&B app. All of the code is linked on the GitHub, and that was. I'm Dynamic Web Page on Twitter. I belong to the Azure Advocates, which is a team at Microsoft that's focused on building out cool things with Azure. So if you have any ideas, let me know. And thank you so much.